We will now partially analyze the SIR model, although we'll never actually fully solve it. So we're looking at the SIR model. There are three variables. But because S plus I plus R equals a constant N, if we can get a handle on S and I, then R is just N minus S minus I. So we'll look at the 2 by 2 system. This for S and this for I. Now, S and I are changing with time. This system is autonomous, meaning that the independent variable doesn't show up in these equations, but time is the independent variable. From calculus 2, if we have parametric equations, x of t and y of t, then the derivative of y with respect to x is the fraction of the time derivatives. And with the exception that we're calling our parametric variables I and S, we're in exactly this situation. DI ds equals DI dt over ds dt. But these derivatives are both given to us. This is this. This is this. So di ds is this fraction. And we'll rewrite this as -1 plus gamma divided by RS. Now we'll integrate both sides with respect to S. I equals the antiderivative of this is negative S. The antiderivative of this is gamma over R times the natural logarithm of S. The number of susceptible people is positive, so we don't need absolute values. And then we have a constant of integration, but this is probably not what you'd expect. The constant of integration is C minus gamma over R times the natural log of S sub 0, where S sub 0 is the initial susceptible population. And let's start by observing that we are allowed to do that. This is some fixed constant. An arbitrary constant minus a fixed constant is still an arbitrary constant. This could be any real number. It really is a totally arbitrary constant of integration. And the reason for writing it in this way is that it will allow us to combine terms. We've got gamma over R in common. And then the difference of two logarithms is the logarithm of the quotient. Now let's take a look at this C. We'll plug S sub 0, the initial number of susceptibles, in to this equation. Over here, we have I of S sub 0 over here The natural log of 1 is 0. So this term vanishes. Now, the thing to bear in mind is that in this model, the number of susceptible individuals is always monotonically decreasing. This derivative is always negative. There are S sub 0 individuals at the start of the outbreak and only at the start of the outbreak. After that, there will be fewer. So the number of infected individuals, when there are S sub 0 susceptible individuals, is the number of infected individuals at the start of the outbreak. So C equals I sub 0 plus S sub 0. The number of the sum of the initial infected population with the initial susceptible population, and I equals negative S plus S sub 0 plus I sub 0 plus gamma divided by R times the natural logarithm of S divided by S sub 0. And the reason we did all this stuff is because we wanted to get an equation where all of our constants had concrete meaning. If we just put in the usual constant of integration here, this C wouldn't have any clear meaning in terms of the biology of the situation. Let's pause to take stock. We haven't solved the system of differential equations. We haven't even solved one of the equations individually. The system of equations and all the individual equations have time as their variable. We don't have time here. And so we cannot answer questions related to time, such as how long will the outbreak last, or when will the outbreak reach its peak. But that doesn't mean we haven't accomplished anything. In the next video, we'll look at the graph of I versus S and see what we can glean from it.